So, very good morning to everyone. So, in the last lecture, we discussed what is linear combination, linear span, linear dependence, and linear independence. And we have seen what is a basis set, right? So, we say a subset of a vector space is said to be a basis set of that entire vector space if this vector set spans the entire V, right? So if it spans entire V and if it is linearly independent, then we say that is a basis set of the vector space. Or in other words, we are looking at a set, the smallest possible set. With that, we can generate the entire vector space. So the smallest possibility can be make sure from the linearly independence. Okay, and the generation can be make sure from the span of V. So these are, if you have these two things on a set, then you can say that that set is a basis set. For example, for R2, the basis set, the standard basis set is nothing but 1, 0 and 0, 1, right? And similarly, you can see there are many other bases for R2, not only just one. If you take B1, this is a basis, standard basis set. And let me take another set B2, which is 1, 1 and 1, minus 1. This is also a basis set of R2. Can have many more. B3, 3, 1, negative 1, 6. So these are all basis set of R2. You can write infinitely many basis set for R2. Similarly, for Rn also you can see what are the basis set. Okay, so here when it comes to standard basis set, we follow some notation. Here, instead of writing 1, 0 and 0, 1, we may write it as E1, E2. That's it. Okay, so here E1, it means here E1 is nothing but 1, 0 and E2 0, 2. All right. Similarly, if you are in R3, so now let me take the standard basis of R3. So those are nothing but E1, E2, E3. Remember one thing, this is a subset of R3, sir. Okay. So when you say it is a subset of R3, each element is coming from R3 only. Okay. So in the earlier case, E1, it means we assumed 1, 0. But in this case, we are going to denote E1 like this. E1 is a triple for which the first element is 1, the rest of the elements are 0. E2 is also triple. Second element is 1, rest of the elements are 0. Similarly, E3. 0, 0, 1. Okay. So even if you take Rn, the standard basis of Rn is nothing but, remember one thing, these are all the basis over the field of real numbers. I'll tell you what is the importance of this field while writing the basis. Okay. Now if you take Rn over R, the standard basis set is nothing but E1, E2 and so on, En. So here E1 is going to be 1, 0, 0, and so on, 0. So you'll have n tuple element here. Similarly, E2, in the second place, you'll keep 1 and rest of the places you'll keep it as 0. So these are the standard basis of Rn. Right. You can find any other basis for R and R3. Similarly for other vector spaces also. But for every vector space, we are going to take some standard basis. Those standard bases are nothing but particularly at one place you will have one, rest of the places will be occupied with 0. Okay, or if you take a subspace, um, we'd like to write the basis of subspace as a combination of these standard basis elements itself. So let me explain what I mean. You take some subset of R2. Let me take some subspace. The subspace is nothing but the line y is equal to x itself. We know y equal to x. This represents a subspace. Okay. Now that subspace can be written like this: set of all x comma x, such that x belongs to real numbers. All right. Now, what is the basis set of this W? Now you know that every element can be expressed in this form. So x comma x. Now you know this x comma x can be rewritten like this: x times 1 comma 1. So every element can be written as a multiple of 1 comma 1. It means 1 comma 1 generates entire W. Right. So therefore, if you look at the basis set has only one element. Basis of W, which is nothing but this singleton set 1 comma 1. Now I'd like to express this basis set with the help of standard basis set. So simply this is how I'm going to write E1 plus E2. So this standard the basis of W is nothing but in terms of standard basis E1 plus E2, because you know E1 is 1 comma 0, E2 is 0 comma 1. If you add those two, you'll get this guy, E1 plus E2. Okay. And here you look at this basis set. You can find something interesting here. So now you know this set is E1 comma E2 only. Whereas when you look at this set, this one can be expressed as a combination of E1 and E2. Why? Because E1 E2 gives you basis of R2. So any element in R2 can be expressed as a combination of E1 E2. So let me express this element 1 comma 1 as a combination of E1 E2. So let me rewrite it here. This one can be written as E1 plus E2, isn't it? And the other one is nothing but E1 minus E2. And this gives you some interesting result. You know, B1 is a basis set, B2 is also a basis set. It means that B1 is linearly independent, B2 is also linearly independent. Now the interesting result here is if V1, V2, if this set is linearly independent, then V1 plus V2, comma, V1 minus V2. This is also linearly independent. We can actually prove it. Starting with this V1, V2 is linearly independent, we can prove that this result is going to be linearly independent. Anyway, I'll take it as a problem, this one. So let me write that problem. Or a theorem, if V1, V2 is linearly independent, then find the relation between A, B, C, D such that the new set, that is A into V1 plus B into V2 and C into V1 plus D into V2, that is linearly independent. Did you understand the problem? If this set is linearly independent, I'd like to see when the linear combination of these V1s is going to be linearly independent. It's like the first element here is a linear combination of V1, V2. The second element is also linear combination of V1, V2. Now, when can it be linearly independent? What is the condition on A, B, C, D? Okay. So let us try to see what is the condition here. Our aim is that we want to have this guy as a linearly independent set. So let me start with a linear combination, that is alpha 1 into A into V1 plus B into V2 plus alpha 2 into C into V1 plus D into V2. Equate the linear combination to 0. So we say a set is linearly independent if the linear combination is 0, implies that all scalars are 0 in that linear combination. Okay, so if we can prove that alpha 1 equal to 0, alpha 2 equal to 0, then we are done. Right. So let me do one thing. Let me rewrite it like this. A into alpha 1 plus C into alpha 2 into V1. To be very specific, let me tell you what are the vector space properties we are using in each step. So this is alpha 1A, alpha 1 AV1 plus alpha 1 BV2 plus alpha 2 CV1 plus alpha 2 dV2 equal to 0. So we came from this step to this step using distributive law of distributive law. So using distributive law, you can write this, right? And again using associativity of multiplication. Okay, so this one can be rewritten like this. It's like alpha 1 AV1 plus using associative property of multiplication and also the commutative property of addition, and again using the distributive property. Okay, so I'm writing this entire expression like this: alpha 1A plus alpha 2C, this into V1 plus alpha 1B plus alpha 2D into V2 equal to 0, right? So many properties we used here using distributive law and the commutative law of addition, and similarly properties related to scalar multiplication. Now we know one thing. What is it? We know that V1 and V2 are linearly independent because that is a statement here. So let us write here. So we know that V1, V2, this set is linearly independent. So when it is linearly independent, if the linear combination is 0, then definitely the scalars must be 0. It means alpha 1 A plus alpha 2 into C equal to 0, and alpha 1 B plus alpha 2 D, this must be equal to 0. Okay. Now the same system can be rewritten like this. So this one can be rewritten like A, C, B, D multiplied with alpha 1, alpha 2. So this equal to 0, 0. So we end up with a linear system, that is A into X equal to 0, right? And this is called homogeneous linear system. And we know this homogeneous linear system has unique solution when A is invertible. Okay. But if A is not invertible, then it is going to have infinitely many solutions in which you can find the non-zero solution. ఇప్పుడు మన ఎయిమ్ ఏంటండి, దీనికి జీరో సొల్యూషన్ ఉందని చూపేయాలా, లేదంటే ఇన్ఫైనైట్లీ మెనీ సొల్యూషన్స్ ఉంటాయని ప్రూవ్ చేయాలా? We want to prove that this set is linearly independent. It means if the combination is 0, we want to prove that this alpha 1, alpha 2 must be 0 only. Means we are expecting that this set, this linear system should have only 0 solution. When it is possible to have only 0 solution here? When the determinant of A is not equal to 0, when that matrix is invertible. Okay, so let me write it here. So Ax equal to 0 has unique solution that is x equal to 0. Let me write. If, of course, you can take it as if and only if. But only if the determinant of A is not equal to 0. So therefore, we can have this alpha 1, alpha 2 equal to 0 provided. So now let me write here alpha 1 equal to 0 and alpha 2 equal to 0 if and only if the determinant of this matrix is 0. ACBD must be equal to, it should not be equal to 0. నేను వెక్టర్స్ని ఇలా రాసుంటే బాగుండేదేమో, ఏ ఇంటూ v1 ప్లస్ సి ఇంటూ v2 అని, అప్పుడు మ్యాట్రిక్స్ ఏబిసిడిలో ఫామ్ అయ్యేది. But anyway, so we end up with a matrix that is ACBD, right? If this determinant is non-zero, then I can say that that linear combination of vectors is linearly independent, right? We created a new set with the linear combination of those vectors. I hope you know what is a determinant, right? So the determinant is nothing but AD minus BC. It should not be equal to 0. So we derived the condition. The question is to derive that condition. If V1, V2 is linearly independent, then find the relation between A, B, C, D such that this set is linearly independent. Now such relation is nothing but AD minus BC equal to 0. It is actually transpose of ABCD matrix. That's why we got the same determinant, AD minus BC. Okay. All right. So now if one set is linearly independent, by taking elements in that set itself, you can create a new set so that which becomes linearly independent. But you need to make sure whatever the linear combinations you're writing, the first combination is independent from the second combination. That is how you need to write. You need to write in such a way that the first element is not dependent on the second. Like that you have to write. Okay. Similarly, there are many problems. We can have it here. So another one. Suppose if this set V1, V2, V3, if this is linearly independent, then I can prove that the other set V1, V1 plus V2, V1 plus V2 plus V3. This is also linearly independent. Okay, so take it as a homework. You try to prove it. If V1, V2, V3 is this set is linearly independent, definitely the other set is also linearly independent. That is given by V1, V1 plus V2, V1 plus V2 plus V3. And let me tell you some other interesting facts about this linearly independence. So if a set is linearly independent, then you look at its linear span. Right. So every element in the linear span can be uniquely expressed as a linear combination of the given vectors. What I mean, you take this set W, which equal to 1, 0, 0, and 0, 1, 0. This is a subset of R3. Okay, and you know the linear span of W is nothing but XY plane. We already did this. All right, and what else you know about this W? This W is linearly independent. This is what you know. Okay, so when it is linearly independent, uh, now my claim is that every element in the linear span of W, in other words, every element in the XY plane can be uniquely expressed as a combination of these two elements. It means that suppose if you take some element, let's say 2 comma 3 comma 0. Okay, now this can be written as a combination of these two only in one way. You can't write it in two different ways. That one way is this. Let's say if you write alpha 1 into 1 0 0 plus beta into 0 1 0, then alpha must be equal to 2 and beta must be equal to 3. This is only the one way that you can express. There is no other alpha comma beta which can give you the same element using these two elements. Okay. Now let me do one thing. Let me take one more W. Let me name this as W1. W1 is nothing but 1 0 0 0 1 0, and this is 1 1 0. Now if you look at the linear span of W, which is nothing but the XY plane only. Okay, but earlier this W is linearly independent, but now it is not linearly independent. Why? Because this third element is a linear combination of first two elements. Therefore, here W1 is linearly dependent. Let me write it as LD. So now this is the vector space. I mean, XY plane you have. We got it from the generation of this W, the linear span of W1, right? But you know W1 is not linearly independent. So in this case, what happens, any element in the XY plane that may not be uniquely expressed as a linear combination of elements here. Means you can express it as a linear combination, but that may not be a unique. For example, let me take this, that is 2, 3, 0, same element. So one possible combination is alpha into 1, 0, 0, or let me take like this, beta into 0, 1, 0 plus gamma into 0, 0, sorry, 1, 1, 0. Now, if you look at alpha, beta, gamma, which gives you 2, comma 3, there are infinitely many such alpha, beta, gamma, not just one. So let me give you one possibility. Alpha equal to 2, beta equal to 3, gamma equal to 0. Okay, and I'll give you one more possibility also. This time I'll take alpha equal to 0. If I take alpha equal to 0, what must be beta? I can tell what is gamma first. Gamma must be 2 and beta must be 1. So if you multiply this with 2, you'll get 2, 2, 0, for which you need to add 0, 1, 0. You'll get 2, 3, 0. That's it. You can have many. You take alpha equal to 5. Accordingly, you can find what is beta and gamma. It is possible. Okay. So if this set is linearly dependent, okay, then if you consider the space generated by that set, every element in that space can be not only, can be expressed as a linear combination of others in infinitely many ways. But the moment it is linearly independent, then uniqueness will come. You can express it only one way, not in infinitely many ways. Okay. So linearly independence guarantees this condition. All right. Okay. Now we have taken definition of basis set, basis of a vector space, right? And of course, I told you, I'll tell what is the importance of this set of all real numbers. Uh, importance of these scalars, right? ఒకవేళ ఫీల్డ్ చేంజ్ చేస్తే మీకు ఏమవుతుందంటే డైమెన్షన్ చేంజ్ అయిపోతుంది. ఐ మీన్ ద బేసిస్ సెట్ అది అయి ఉండకపోవచ్చు. Let us see what is the importance of this field set. So suppose if I take R2 over R, R2 over R, this is my vector space. So set of all real numbers over set of all vector elements in R2 over the field of real numbers. Now, if you look at the basis set here, let me name the set B. So B equal to 1, comma 0 and 0, comma 1. So it is very clear that this B is a basis. Basis of R2 over R. Okay. Now my question is, if I take this, the vector space as R2 over Q. Okay. Can this B be basis of R2 over the field of real numbers? Sorry, over the field of rational numbers. Can someone reply? If B and A set to over the field of rational numbers పైన బేసిస్ అవుతుందా? కండిషన్స్ ఏంటండి? బేసిస్ అవ్వాలంటే లీనియర్లీ ఇండిపెండెంట్ అవ్వాలి, అట్లాగే స్పాన్ చేయాలి కదా. ఇది ఎట్లాగా లీనియర్లీ ఇండిపెండెంట్ అవుతుంది, దాంట్లో డౌట్ లేదు. మరి స్పాన్ చేస్తుందా? అంటే R2లో ఏ ఎలిమెంట్ అయినా సరే ఈ 1,0,0,1 తీసుకుని అలాగే రేషనల్ నెంబర్స్ తీసుకుని ఇట్లా కాంబినేషన్ గా రాయడానికి అవుతుందా? లెట్ మీ టెల్ యూ వాట్ ఐ మీన్. You need to pick up this alpha from rational numbers, beta from rational numbers only. Okay. So now, is it possible to express any element x comma y as a combination of alpha into 1 comma 0 plus beta into 0 comma 1? అంటే ఎగ్జాంపుల్కి ఇది తీసుకోండి, √2 కామా √2 కామా 1 తీసుకోండి. √2 కామా 1 తీసుకుంటే we know this set is linearly independent. When the set is linearly independent, just now we observe that every element in the space which is generated can be uniquely expressed as a combination of these elements. Okay, and ఇప్పుడు ఈ √2, 1 ఈ రెండిట్లో ఒక లీనియర్ కాంబినేషన్ గా రాద్దాం అనుకుంటే అది యూనిక్ అవుతుంది. అండ్ దట్ కాంబినేషన్ ఇస్ నథింగ్ బట్ √2 into 1, 0 plus 1 into 0, 1. This combination only will give you this element √2, 1. But here, if you observe that this √2 which doesn't belongs to Q. √2 doesn't belongs to Q. And moreover, this √2, 1, this is an element of R2. It is there in R2, but I am unable to express this as a combination of 1, 0 and 0, 1 with the help of rational numbers. నేను దీని లీనియర్ కాంబినేషన్ ఆఫ్ 1, 0, 0, 1 కావాలంటే నాకు ఖచ్చితంగా ఇర్రేషనల్ నెంబర్ √2 కావాల్సింది ఆ సెట్లో. కానీ రేషనల్ నెంబర్ సెట్లో √2 అనేది అవైలబుల్ లేదు. ఓకే, therefore this set B cannot be basis over the field of rational numbers. ఇప్పుడు ఏం లేదు సార్, మొత్తం వెక్టర్ స్పేస్ ని మీరు తీసుకెళ్ళడానికి జస్ట్ ఈ బేసిస్ సెట్ ని స్కాలర్ సెట్ ని క్యారీ చేస్తే సరిపోతుంది. ఇప్పుడు నా ఎయిమ్ ఏంటంటే R2 ని జనరేట్ చేయాలి, కానీ మీ దగ్గర ఉన్న ఫీల్డ్ సెట్ రేషనల్ నెంబర్సే అనుకుందాం. ఇప్పుడు జస్ట్ రేషనల్ నెంబర్ ఫీల్డ్ తోటి మనం మొత్తం R2 ని జనరేట్ చేయగలమా? అంటే మీకు ఇక్కడ 1, 0 ఉంది, 0, 1 ఉంది. రేషనల్ నెంబర్స్ తోటి మల్టిప్లై చేసి వాటి యొక్క లీనియర్ కాంబినేషన్ తీసుకుంటే you will get all x comma y for which x is a rational number, y is a rational number. Are you getting it? Try to understand one thing. The linear span of this B over Q, that is equal to set of all x comma y, right? Set of all x comma y such that x comma y both belongs to rational numbers only, which is not equal to R2. It means that this set is not giving you the entire R2 over the field of real numbers. Whereas if you look at the linear span of B over the field of real numbers, what happens here? That gives you x comma y such that x comma y belongs to real numbers, which is nothing but R2. Okay, so earlier, now I can say that this set B is a basis set for R2 over R, but B is not a basis set for R2 over Q. So clearly concluded here. So therefore we can conclude that, so the conclusion is B is not a basis set for R2 over the field of real numbers. Sorry, or R2 over the field of rational numbers, not the real numbers. But B is a basis for R2 over R. Okay, so that's why field is also important. మనం జనరల్గా ఈ ప్రాబ్లమ్స్ అన్ని చేసేటప్పుడు ఫీల్డ్ సెట్ ఆఫ్ రియల్ నెంబర్స్ కింద ఎస్యూమ్ చేసుకుని వెళ్ళిపోతామండి. అక్కడ మెన్షన్ చేయలేదంటే ఫీల్డ్ రియల్ నెంబర్స్ అని తీసుకుంటున్నామని అర్థం. ఈ బేసిస్ కానీ ఇవన్నీ మనం మాట్లాడే కాంటెక్స్ట్ రియల్ నెంబర్ కాంటెక్స్ట్ లోనే మాట్లాడుతున్నాం. ఓకే, ఐ విల్ గివ్ యూ స్మాల్ ఎక్సర్సైజ్ and I don't answer this question now. You please think. Okay, can you tell me what is the basis set for R over R? Okay, first one R over R, and second one C over R, and the third one C over C. Okay, and the fourth one C over Q, and fifth R over Q, right? And similarly sixth one Q over Q. Now try to think what can be the basis set for each vector space which is given here. And we also discussed what is the dimension, number of elements in the basis set. Number of elements in the basis set is called dimension. Now I'm telling you that the dimension of okay, first one I'll answer it. So the first one basis set B, which is nothing but just 1. One ane kadandi, any non-zero singleton set can be a basis set of R over the field of real numbers. అంటే మీకు యాక్చువల్గా స్కేలార్ బ్యాగే రియల్ నెంబర్స్ ఉంది, వెక్టర్ సెట్ కూడా అదే. సో ఇప్పుడు నాకు జస్ట్ 1 అనే ఎలిమెంట్ ఇస్తే నేను జస్ట్ ఎవ్రీ ఎలిమెంట్ 1తో మల్టిప్లై చేస్తాను. ఇప్పుడు నాకు 5 కావాలనుకోండి, స్కేలార్ బ్యాగ్ నుంచి 5 తీసుకుని 1తో మల్టిప్లై చేస్తా. 5 into 1 ఇట్ గివ్స్ మీ 5. ఒకవేళ అలా కాదు, బేసిస్ సెట్ సింగిల్టన్ 7 తీసుకున్నారు అనుకోండి, ఇఫ్ యూ వాంట్ 5, స్కేలార్ సెట్లోంచి 5/7 తీసుకోండి, మల్టిప్లై చేయండి. 5/7 into 7 will give you 5. Okay, so any non-zero singleton set becomes a basis here for the first one. Now if you ask me what is the dimension of R over R, I'll say this is 1. Why? Because there is only one element in the basis set. Okay, similarly you think what will be the basis set here? అమ్మా ఇక్కడ మీరు తీసుకునే కాంప్లెక్స్ నెంబర్స్ తీసుకోవాలి, ఎందుకంటే మీ వెక్టార్ సెట్ కాంప్లెక్స్ నెంబర్ సెట్. But remember one thing, every real number is also a complex number. What I mean, every real number belongs to the set of complex number set. If you take 1 can be expressed as 1 plus 0 into I. This is what I mean. Okay, so think about this question. I leave it as an exercise. I don't answer it today. Anyway, there is one statement here. So you came to know what is basis set, right? Now it is time to write a statement. If you take a vector space and its basis set, then every element in the vector space can be uniquely expressed as a linear combination of elements in the basis set. Do you understand this statement? So you try to understand. Here you are given with some set B which has n elements. Cardinality of B is n elements. Now This is a basis set of a vector space over some field. Then each vector in V can be uniquely expressed as a linear combination of vectors in this set. Okay, so this is Sama saying that every element in the vector space can be uniquely expressed as a linear combination of elements in the basis set. So that is the statement they are giving. And before that, we proved every element in the vector space can be uniquely expressed as a linear combination of elements vectors in the linearly independent set. Assume that vector space is generated by linearly independent vectors. Okay, and let me introduce what is the dimension here. And before that, one more observation. One more observation is this. Any two bases of a vector space consist of the same number of elements. Okay, so if you want to prove this result, you can do one thing. I'll give you hint how to prove it. So you take one basis set of V with n elements. So number of elements in B, or in other words, you take it like this: V1 equal to V1, V2, and so on Vm. Assume that this is a basis of V. Okay, and similarly, you start with another basis set that is U1, U2, and so on Un, and you assume that this is another basis of V. Okay, so our aim is to prove that M is equal to N. If we can prove M equal to N, then we are done. So you can prove it like this. You know B1 is a basis, so every element in V can be expressed as a linear combination of these VIs. So therefore, each VI can be expressed as a linear combination. Sorry, each UI can be expressed as a linear combination of VIs. Okay, and try to express it and make use of the fact that both sets are linearly independent. So from that, you'll come up with a linear system homogeneous linear system, right? From which you can come to know that M equal to N. Okay, take it as an exercise. If you don't get it, I'll discuss it in the next class. All right. Anyway, I have 10 minutes time only, so let me give you the definition of basis set. And before that, you have some interesting facts. You know, those interesting facts are, this is one, that is, if basis contains n number of elements, if you find that there are n elements in the basis set, you take any subset of the vector space which contains more than n elements, then that set is going to be linearly dependent. Try to understand. If basis set has n elements, then any set which contains more than n elements is linearly dependent. Let me explain you with a simple example, V1, V2. Let me assume this B is a basis of V. Okay, now I would like to prove that any subset, that is U1, U2, U3, which is clearly subset of V, So I would like to prove that this set is linearly dependent. ఎందుకు లీనియర్లీ డిపెండెంట్ అంటున్నామండి? ఇక్కడ బేసిస్ లో యాక్చువల్గా 2 ఎలిమెంట్స్ ఉన్నాయి, కానీ సబ్సెట్ లో 3 ఎలిమెంట్స్ ఉన్నాయి. సో మనం ప్రూవ్ చేయాల్సింది ఏంటి? బేసిస్ సెట్ లో n ఎలిమెంట్స్ ఉంటే మీరు వేరే ఏదైనా సబ్సెట్ తీసుకోండి వెక్టర్ స్పేస్ కి, దాంట్లో n కంటే ఎక్కువ ఎలిమెంట్స్ ఉంటే అది ఖచ్చితంగా లీనియర్లీ డిపెండెంట్ అవ్వాలి అంటున్నారు. సరే, ఎందుకు అవ్వాలి సార్? ఒకవేళ నేను లీనియర్లీ ఇండిపెండెంట్ అని అజ్యూమ్ చేసుకుంటా అన్నారు. సరే, అజ్యూమ్ చేసుకోండి. we'll say that this is wrong, and we'll assume that this set is linearly independent. Okay, if this set is linearly independent, u1, u2, u3. Okay, now can you extend this set to a basis set? అంటే నేను ఈ సెట్ కింద కన్వర్ట్ చేయగలరా అని నేను అడగట్లా. ఇది లీనియర్లీ ఇండిపెండెంట్. మనకి ఇంకో కావాల్సిన కండిషన్ ఏంటండి? ఇది ఒకవేళ మొత్తం వెక్టర్ స్పేస్ ని స్పాన్ చేస్తే బేసిస్ సెట్ అయిపోతుంది కదా. లెట్స్ అస్యూమ్ దట్ ఇట్ స్పాన్స్. ఒకవేళ స్పాన్ చేయట్లేదు అన్నారు అనుకోండి, దాని అర్థం ఏంటి? దెర్ ఈస్ సమ్ వెక్టార్ ఇన్ ద వెక్టార్ స్పేస్ which cannot be expressed as a linear combination of these three. అంటే ఇంకా ఇప్పుడు ఏం చేయవచ్చు? You found one more guy, let me assume that is u4, which is not depends on u1, u2, u3. Then you include that guy in this set, u1, u2, u3, u4. Now this set becomes linearly independent. ఒకవేళ ఇది స్పాన్ చేసింది అనుకోండి, ఇది లీనియర్లీ ఇండిపెండెంట్ అని తెలుసు. If you know if it spans the vector space, then definitely it becomes a basis set. ఎక్కడో ఒక స్టేజ్ దగ్గర కంపల్సరీ ఇదైనా బేసిస్ అవ్వాలి. ఒకవేళ ఇది మీరు లీనియర్లీ ఇండిపెండెంట్ అనేది ఎజ్యూమ్ చేసుకుంటే, ఆ ఎక్స్ట్రా కండిషన్ స్పానింగ్ అనేది సాటిస్ఫై అయితే ఇది బేసిస్ అవుతుంది. ఒకవేళ స్పాన్ చేయట్లేదు అనుకోండి, యూ కెన్ ఫైండ్ వన్ గై హూ డస్ నాట్ డిపెండ్స్ ఆన్ దీస్ గైస్. ఆయన ఎవరైతే ఉన్నారో ఆయన ఇక్కడికి వచ్చి తీసుకొచ్చి కూర్చోబెట్టండి సెట్లో, అప్పుడు కూడా ఇది లీనియర్లీ ఇండిపెండెంట్ అవుతుంది. స్పాన్ చేస్తుందో లేదో చూడండి. స్పాన్ చేస్తుంది అనుకోండి, బేసిస్ అంటాం. ఇఫ్ ఇట్ డజంట్ స్పాన్, ఇట్స్ నాట్ ఎ బేసిస్. స్టిల్ ఇట్ ఈస్ లీనియర్లీ ఇండిపెండెంట్. దెన్ దిస్ లీనియర్లీ ఇండిపెండెన్స్ ఇస్ గెటింగ్ బిగ్గర్ అండ్ బిగ్గర్ అండ్ బిగ్గర్. It means that the number of elements in the basis set are increasing. Is it possible? It's not possible, because just now we have seen that any two basis set will contain same number of elements. ఖచ్చితంగా ఇది లీనియర్లీ డిపెండెంట్ అయి తీరాల్సిందేనండి. సార్ నాకు ఇట్లా కుదరదు సార్, నాకు ఇట్లా ప్రూవ్ చేయండి సార్ అంటే ఎట్లా ప్రూవ్ చేస్తాం? లీనియర్ కాంబినేషన్ తీసుకొని if you can find at least one alpha which is non-zero, then we can say that this set is linearly dependent, right? Okay, so let me try to prove that in that way only. Alpha 1 v1, not v1. We want to prove this set is linearly dependent, provided v1 and v2 is a basis set. So alpha 1 u1 plus alpha 2 u2 plus alpha 3 u3 equal to 0. Okay, and we know one thing, this v1 v2 gives you a basis of v. Therefore this u1 can be written as some a11 plus a11 into v1 plus b11 into b12 into v2. Is it good to write that way? So this u1 can be expressed as beta 1 v1 plus beta 1 2 v2, and u2 can be expressed as some beta 21 v1 plus beta 22 v2, because it is a basis set. Okay, and u3 can be expressed as beta 31 v1 plus beta 31, this is 32 v2. All right. Now substitute these u1, u2, u3s here. Amma idi b, I mean b అనేది basis అవుతుంది కాబట్టి నేను u1, u2, u3 ఇట్లా ఎక్స్ప్రెస్ చేయగలిగా. Now if you substitute everything here, you can see what is the coefficient of v1. So that is alpha 1 beta 1 1. అలాగే ఇక్కడ ఒక v1 ఉందండి, ప్లస్ alpha 2 beta 2 1 ప్లస్ alpha 3 beta 3 1. This into v1 plus what will it be? So this is alpha 1 into beta 2 1 plus alpha 2 into beta 2 2 plus alpha 3 into beta 3 2. This into v2 equal to 0. Okay, so here the linear combination is 0. So this implies that the scalars are also 0. Why? Because v1 comma v2, these are linearly independent. So when these are linearly independent, then definitely this alpha 1 beta 1 1 plus alpha 2 beta 1 2. So let me write that entire guy like this instead of this lab equal to 0. Similarly, alpha 1 beta 2 1 plus lab equal to 0. Okay, now this one can be written in terms of a matrix. Now the matrix is beta 1 1 beta 1 2 beta 1 3, and this is beta 2 1 beta 2 2 and beta 2 3. So this matrix multiplied with alpha 1 alpha 2 alpha 3. So this will give you 0 0 0. The same linear equations I have written in terms of matrices. Okay, now you end up with this guy, that is ax equal to 0. The linear system ax equal to 0, but here A is not a square matrix, which is a rectangular matrix. Now the question is whether this set has unique solution or infinitely many solutions. దీన్ని జామెట్రికల్ గా చూడండి. మీరు ఈక్వేషన్స్ లో చూస్తే ఇన్వెస్టిగేషన్ డిఫికల్ట్ అవుతుంది. జామెట్రికల్ గా చూడండి. ఇది ఏబిసి అని తీసుకుని ఇవిడి గారిని XYZ అని తీసుకున్నారు అనుకోండి, అంటే ఈక్వేషన్ ఏమవుతుంది? ఏఎక్స్ ప్లస్ బివై ప్లస్ సిజెడ్ ఈక్వల్ టు 0. దట్ ఎగ్జాక్ట్లీ రిప్రజెంట్స్ ఎ ప్లేన్ పాసింగ్ త్రూ ఆరిజిన్. అంతేగా? అంటే ఇక్కడ మన ఫస్ట్ ఈక్వేషన్ మీరు అబ్జర్వ్ చేస్తే, this is a plane passing through origin. This is one plane and this is another plane. Both are passing through origin. Now what you are doing is you are taking two planes which are passing through origin. What is their intersection? Do they intersect first of all? Intersect అవుతాయండి బాబా? Two planes passing through origin.
Yes.
ఇంటర్సెక్షన్ ఏమవుతుంది?
At 0, 0, sir.
మొత్తం
లైన్ పాసింగ్ త్రూ
0,0,0 ఇంటర్సెక్షన్ ఏంటయ్యా?
లైన్ పాసింగ్ త్రూ ఆరిజిన్ సార్.
Come again. Exactly. So if you take two planes passing through origin, their intersection will be a line passing through origin. Okay, so here, so intersection of these two planes is a line. Now it means every point on this line, that is alpha 1, alpha 2, alpha 3, you take any point which is there in this line. This line is given by intersection of these two planes. So every point on this line satisfies this equation, that is Ax equal to 0. It means this linear system has infinitely many solutions. This has infinitely many solutions. So since it has infinitely many solutions, it means non-zero solution is also available. 0, 0, 0 always solution అవుతుంది. కానీ ఇక్కడ మనకి ఇన్ఫైనెట్లీ మెనీ సొల్యూషన్స్ ఉన్నాయని తెలుసు కాబట్టి, అంటే జీరో కాకుండా వేరే సొల్యూషన్ కూడా ఉంది, అంటే నాన్ జీరో సొల్యూషన్ ఉంది. ఇట్ మీన్స్ యూ కెన్ ఫైండ్ ఆల్ఫా 1, ఆల్ఫా 2, ఆల్ఫా 3 ఇన్ విచ్ అట్లీస్ట్ వన్ ఆఫ్ దెమ్ ఇస్ నాన్ జీరో, రైట్? అండ్ దిస్ ఇస్ వాట్ వీ వుడ్ లైక్ టు ఫైండ్. I hope we are done with the proof. So we came to know that this linear system has a non-zero solution. It means it is possible to find a linear combination that is equal to 0, but not all scalars are 0. So let me write it here. This has non-zero solution. So it has non-zero solution. This implies that this set u1, u2, u3, this set is linearly dependent. Okay, మీకు ఇందాక any two bases of a vector space has same number of elements, దానికి ప్రూఫ్ ఇలానే చేయొచ్చండి. ఒక సెట్లో m అని తీసుకొని ఇంకొక సెట్లో హైయర్ తీసుకోండి, రైట్? ఎగ్జాంపుల్ డైమెన్షన్ 2, బట్ నేను 3 అని తీసుకుంటున్నా. బేసిస్ సెట్లో 3 ఎలిమెంట్స్ ఉన్నాయని తీసుకున్నాను. సో ఇప్పుడు బేసిస్ సెట్లో మీకు 2 ఉంటాయని తెలిసి మళ్ళీ ఒక కొత్త సెట్లో 3 తీసుకున్నారు. అప్పుడు ఈ కొత్త సెట్ ఏమవుతుంది? ఖచ్చితంగా డిపెండెంట్ అయిపోతుంది. దట్ ఈస్ వాట్ వీ ప్రూవ్డ్ హియర్. If the basis set has n elements, then you take any set which contains more than n element, that set is linearly dependent. ఇంకా బ్యూటిఫుల్ ఫ్యాక్ట్ ఏంటంటే ఇక్కడ, you know what is the dimension of the vector space, right? So the dimension of the vector space is nothing but, so let me write dimension of V over F we are going to denote the dimension as just dim. Okay, let me write it here. Dimension of V over the field F. That is nothing but number of elements in the basis set. So number of elements in the basis set of V, which is called dimension of V. So now it is very clear that dimension of R2 over the field of real numbers, you can see that is 2. And similarly, the dimension of R3 over the field of real numbers, which is 3. Now, just now we proved one statement. Statement is that if there are n elements in the basis set, you take any set which contains more than n elements, that is linearly dependent. And ఇప్పుడు మీరు R3లో ఏదైనా 3 ఎలిమెంట్స్ సెట్ తీసుకున్నారు అనుకోండి, ఏమీ చేయకుండానే డైరెక్ట్గా మీరు లీనియర్లీ డిపెండెంట్ అని చెప్పేయచ్చు. అంటే ఎగ్జాంపుల్కి యూ టేక్ 1, 2, 3, 4, 5, 6. You take this set. I know this is a subset of R2. and I know what is the dimension of R2. The dimension of R2 is 2. It means basis set will have only 2 elements. But here this set contain more than 2 elements. 3 elements ఉన్నాయండి ఇక్కడ. So what is the conclusion? This set is linearly dependent. Okay. అట్లాగే R3 లో సబ్సెట్ తీసుకోండి. 1 2 1 3 1 1 1 0 minus 1 5 10 minus 2. I have randomly written this set. Okay. Now this is a subset of R3, and you know the dimension of R3 is 3. This set contains more than 3 elements. Therefore, this set is linearly dependent. Okay. Yeah. Any linearly independent set can be extended to basis set. Let me stop the class with that statement. That's it. Any linearly independent set of a vector space can be extended to a basis set. అంటే ఒక సెట్ లీనియర్లీ ఇండిపెండెంట్ అయిందండి, అది స్పాన్ చేస్తే బేసిస్ అంటారు. స్పాన్ చేయలేదు అనుకోండి, అంటే స్పాన్ చేయట్లేదు అంటే ఏదో ఒక ఎలిమెంట్ 2 ఎలిమెంట్స్ తగ్గుంటాయి. ఆ 2 ఎలిమెంట్స్ ఆర్ 1 ఎలిమెంట్ ఇంట్రడ్యూస్ చేయడానికి ట్రై చేయండి. I'll give you an exercise related to this question. Find a basis set of R3. Find a basis set of R3 which contain one comma 1. It means this is what we require. We need a basis in which 1 comma 1 is one number and v2 v3 are remaining 2 numbers. You try to find v2 v3. This is the question. Find v2 v3 in such a way that this set becomes basis set. That's it. Okay, try to think about this question. We'll answer it tomorrow. Anyway, I'll stop it here. Let me know if you have any questions or doubts.